All right, so this chapter, we're in starting chapter 5, and probably this is the most important chapter that we are going to cover. It's very foundational. Obviously, probably chapter 1 is pretty important too, but the concepts in chapter 1 are pretty simple and easy to understand on the basic level. This chapter is also critically important, but it's also more difficult than chapter 1, and it may be probably the most difficult chapter we've done so far. So I would highly recommend you spend an adequate amount of time to make sure you understand the concepts here and also how to solve these problems. So these problems are going to come up again once we get into the test 3 material. And if you're not comfortable with the problems in this chapter, especially at the end, in the general idea that we're working with the normal model, then probably the test 3 material will be harder than it needs to be. So just make sure you're practicing enough to where you're pretty comfortable with this, and then it'll make things a lot easier later on. So what we're doing in this chapter is we're gonna talk, in the beginning at least, how to compare two quantitative variables. Like, how can we put two quantitative variables on the same scale, basically? So this example that we have here, Thompson took the gold in the Olympics with a long jump of 6.58 meters for the women's heptathlon, 0.41 meters higher than average. So that's a good jump. Johnson won the 200-meter run with a time of 23.26 seconds, 1.32 seconds faster than average. So that is also good. If you're in a run, you want to be faster than the average. So whose performance was more impressive? So if you notice these two variables, they're both quantitative. That's what we're going to be working with in this chapter. The long jump is measuring distance, and the higher the number, the better. You obviously want to have a longer jump than a shorter jump. And with the run is measuring time. And with time, you want it to be shorter. So long jump, distance, and a bigger number. The run, time, and a smaller number. So we have two different measurements, and we have two different parameters for determining which is good or which is bad. So how do we decide who did better? So one way to do this is if we look at the long jump, and let's figure out how far we are measured in standard deviations. So we can make that a common measurement between the two. So there's no way to convert seconds to meters or vice versa. But we can talk about this in standard deviation. So if we look at one standard deviation above for the long jump, so let's take the mean, and we're talking above the mean. So that's what we're talking about. When we say above, we're implicitly saying above the mean. So the mean is 6.17. If we add the standard deviation, 0.247, we get 6.417. And so we're not quite to the individual distance of 6.58. So let's add it again, or go 2 standard deviations above the mean. And so that would be 6.17 plus 2 times 0.247. And that will give us 6.664. And so now we've just gotten a little bit above it. So we could say that the long jump is just shy of 2 standard deviations above. I'll just write above, but we mean above the mean. All right, now let's look at the run. So the 200-meter run, we'll do the same thing, but now we're going to subtract because the individual time is below the mean. So let's go 1 standard deviation below the mean. So 24.58 minus 0.654, and that is 23.926. And then we're not quite there yet. Let's do it again. So 24.58 minus 2 times 0.654, and that is 23, apologize for that, 0.272. And now we're not quite there. We're still a little bit above the individual time, but we're pretty close. If we did 3, we'd be far below it. So let's say that this one, because it is below, it's more than 2 standard deviations below. So let's say just over 2 standard deviations below. And so just going with that, we can see that this one is farther away measured in standard deviations. It's farther from the mean measured in standard deviations. So that tells us that that would be the better performance for that event compared to the long jump distance. But that's a very clunky way to do it, I guess. We could probably find a better way to do it. And also, if this one was also just less than 2 standard deviations away, then how would you figure it out? Because if they were both about just under 2 standard deviations, then it's hard to see exactly which one. And maybe they're the same, but maybe they're not. So let's talk about a more precise way to do this and a quicker way. So this is called the z-score. And so what the z-score does is it finds the exact distance between the value and the mean in standard deviations. And so we have a formula that we can use. So z equals x minus, now we're going to use this Greek letter u, and we're going to use this Greek letter sigma. So in this case, z, of course, is the z-score. X is going to be a data point. So an exact, precise individual data point. That Greek letter is called mu, if you've never seen that before. And kind of looks like a cursive U or maybe an M, depending on how you look at it. But this is going to be the population mean. And then this Greek letter is called sigma, and it is the population standard deviation. So we're going to subtract the mean, we're going to divide by the standard deviation, and that will tell us how far that data point, x, is from the mean measured in standard deviation. So now we can take any quantitative data point from a quantitative population and see where it compares to other data points from a different population. So this is called the z-score. So the z-score measures the distance of the value or the data point from the mean in standard deviations. So a positive z-score, so if we calculate this and we get a positive number, the data point is going to be above the mean. So if this is positive, then obviously x has to be more than mu. Negative means that x has to be smaller than mu. Small z-score, now what would that mean? So that would mean that this difference would be very small, so x would have to be close to the mean. And then conversely, a large z-score would mean the value is far from the mean. So the large z-score either means that you did really well or really poorly compared to everyone else. And we'll talk about how far, like what would be considered a large z-score. So like would 10 be a large z-score? Would 5 be a large z-score? Or do we have to get all the way up to 100, or what is it? So we'll talk about that as we go. So let's precisely calculate the z-scores for these events. So for the long jump, the z would be 6.58 minus 6.17 over 0.247, and we calculate that, and we get about 1.66. So that jump, 6.58 meters, is 1.66 standard deviations above the mean. So it's a good idea to keep that in mind, what exactly this is telling us. So 1.66 standard deviations above the mean. Then if we do the 200-meter run, do the same thing, and we have 23.26 minus 24.58 over 0.654. And with that, we get negative 2.02. And so with that, we could say 2.02 standard deviations below the mean. So we don't have to write the negative because we're going to state it's below. And like we said on the last page, the positive and the negative don't matter as far as determining which is more impressive, as long as we're on the good side of the mean. So the long jump is on the good side of the mean because it's higher. The run is on the good side of the mean because it's lower. And so other than that, the negative or the positive doesn't matter. So which one's more impressive? The one that is farther from the mean in the right direction. So this one is going to be because 2.02 is more than 1.66. So we're not worried about the negative, other than obviously if the run had a positive z-score, that would be bad because then you'd be slower than the mean. So that would not be a good time. So that's the idea, and we'll see how to use this a little bit later in the third video, I think, for the chapter. But that's kind of the initial concept we want to learn.